All right, let's talk about London Dispersion Forces. London Dispersion Forces is the weakest of the three intermolecular forces. We've got hydrogen bonding, which is very strong, dipole-dipole interactions, which is medium strength, and then we've got London Dispersion Forces, which is the weakest intermolecular force. Now, I like to think of this as the consolation prize because everybody gets it. If a molecule has electrons, it is going to experience London dispersion forces to some extent. Let's watch this analogy that I've prepared, and then we'll get back to the slides. I want to show you an analogy for the van der Waals force, and that is static electricity. So I've got a couple of balloons here. One's large and one's kind of smaller. And if you rub this on your hair, you can sometimes get this to stick to a wall. And it's easier to get the large balloons to adhere to the wall. There are electrons in atoms that make up all materials. This door, for example, and the carbon atoms and hydrogen atoms in this rubber balloon. So, of course, my hair sticks to the balloon through static electricity. And you can think of that as van der Waals attractions too. Any two surfaces that are made up of electrons are going to be attracted to each other if they're in very close proximity. The electrons from one atom will be attracted to the protons or the nucleus of the other positively charged nucleus of the atoms. And the electrons of that atom will be attracted to the protons or positive nucleus of the atoms in the other surface or molecule. Okay, so let's try this. We'll put this on the wall and see what happens. I couldn't get that balloon to adhere to the wall. Now, a smaller balloon is even more challenging because there's just less of a surface to grab onto or to hold onto. So that just falls off extremely quick and fast, all right? The same principle applies to rock climbing or mountain climbing. You want to have as much surface on a rock or a rock cliff as you're climbing up. Usually you always want to have 3 points of contact and you're only moving one hand at a time or one leg at a time off the surface. So you can have 3 points of attachment and a greater adherence, right, to the cliff face so you don't fall off. Now let's begin to think about molecules. Now these molecules here, you cannot see the electron cloud that forms this molecule. This is methane. We have carbon in the middle and 4 hydrogens, but this is basically a small sphere like that balloon. And here's another methane molecule, okay? So you just kind of have to imagine that these are just spheres, an orange or something in your house that's spherical, okay? And they're gonna have a certain amount of surface area that can allow these two molecules to attract one another, okay? And that would be your London dispersion forces we're talking about. Now, larger molecules like this butane is a liquid if it's cooled down to low temperatures, and that's in your cigarette lighters. The reason why this is a liquid is because the surface area is much greater, okay? You have a lot more carbon and hydrogen atoms for there to be more of a surface. So you can kind of imagine this being a cylinder, more like a cylinder shape, okay? You've got an electron cloud of all of the carbon and hydrogen atoms kind of forming a circle in this dimension, and then you can see how it's very long, okay? So the surface area of this electron cloud of the whole molecule versus the electron cloud of this molecule are going to be different, okay? The larger the surface area, the more this can adhere to other molecules in solution or as a solid, okay? So this has a greater surface area because it has a larger mass, okay? It has more atoms in there, and so it's going to have a greater London dispersion forces attraction with other molecules. Now this molecule here and this molecule here both have the same number of carbon and hydrogen atoms. Now this molecule here, we can just call it isobutane if that's okay. This is a different molecule now where still you have 4 carbon atoms, okay, and a bunch of white hydrogen atoms. These little white plastic balls are the hydrogen atoms. And this molecule here has the same mass, right? It has the same molecular formula, but look at its geometry. It's more crunched up and crumpled up like a watered up piece of paper. And so its surface area is going to be less because it's a spherically kind of shaped molecule, okay? So this is more branched, it's more compact, it has less surface area compared to what I showed you before, which is a straight chain alkane. So this is what we call a straight chain when it's all kind of in a zigzag line there. And this has a greater surface area because the carbon atoms are kind of more spread out, okay? So if you have more surface area, there's going to be a greater London dispersion forces, and that molecule is going to have a higher boiling point than if something's more compact. Obviously, something that is lower molar mass is going to be more compact. When you have two molecules of equal molar mass, you need to consider which one might have a greater surface area based on its molecular structure, okay? So I hope that analogy with the balloons kind of helps you. The larger the balloon, it's going to stick to the wall a little bit better. And that's the same way with molecules because it has a greater surface area, okay? There's just more surface for the electrons to be induced to polarize and distribute asymmetrically, all right? Okay, so that's a good analogy of the London dispersion forces. And without getting into a lot of math and physics, that's basically all you need to know about it, okay? The larger the surface, the more London dispersion forces a molecule will have. So again, it's simply due to opposites attracting. So we've talked about dipole forces, where you have a polar molecule with a very obvious unsymmetrical distribution of charge, where one of the atoms is partial positive, one of the atoms is partial negative, and there's a clear reason why two molecules that are polar should be attracted to one another. And that's the dipole-dipole force. Now, in contrast, the London dispersion forces is a transient, very weak electrostatic attraction between two molecules because the electrons from one molecule will be attracted to the positive parts, the nuclei, right? The nucleus is positively charged because of the protons. So the electrons will be attracted to the nuclei of other atoms and vice versa, okay? Again, it's just opposites attract. So I've got a drawing here of it looks like a diatomic molecule. We could call that nitrogen, for example. And you've got delta plus and delta minus parts of the molecule. We're not attributing that to a certain bond or a type of element. Anything's going to have London dispersion forces, and it's just that side of the molecule that's touching the other side. The electrons repel one another, so you create this unsymmetrical distribution of charge at an instant just simply due to the fact of electrons scooting around and moving so quickly, okay? So that's your London dispersion force. All right, it's a very fuzzy kind of picture. It's hard to put your finger on. It's hard to depict it and draw it, okay? So let's talk about the requirements for London dispersion forces. So once again, all molecules, because they're made of electrons, can exhibit or display London dispersion forces. Keep in mind that the greater the surface area, the greater the intramolecular force. Let's work on a few problems just to get a feel for this. Okay, in this first problem, we're asked to identify which of these is expected to have London dispersion forces, okay? And this is a bit of a trick question, but just remember, all molecules that have electrons are going to have London dispersion forces. So neon, it has, electrons. Oxygen, water, selenium dichloride, these are all substances with electrons, so they are going to display London dispersion forces in some extent, all right? If you had a molecular hair, you could rub it on your hair and then stick one molecule to another. You could think of it like that, okay? It's probably a bad analogy at this point. But anyway, they have electrons. Our next problem says, which one of these is expected to have the greatest London dispersion forces? And we look at F2, Cl2, Br2, I2. These all have two molecules. They're all diatomic. So what do we do here? We want to think about surface area, which scales with size, and we want to think about the atoms in the periodic table. As you move down the periodic table, atoms become larger in size. So fluorine, chlorine, bromine, and iodine are going to be relatively sized like that. Iodine is going to be the largest atom. Because of that, the iodine molecule is going to become quite large in comparison to the fluorine molecule. So we would expect iodine to have a larger surface area, a greater surface area, and therefore have the greatest London dispersion forces. Okay, so remember your trend of atomic size. They increase as you move down the periodic table, and atoms increase as you move to the left of the periodic table. The larger the size, the larger the surface area, and therefore the greater London dispersion forces. This next question says, which one of these molecules is expected to have a higher boiling point? Now keep in mind the bigger, larger surface area is going to have a higher intermolecular force, and that corresponds with a higher boiling point. Okay, so if we just look at these molecules, CH4, C2H6, C8H18, and H2, C8H18, that's octane or gasoline, by the way, has 8 carbon atoms and 18 hydrogen atoms. So that's going to be a rather big molecule with a large amount of surface area that can stick or grab on to other molecules. Okay, so C8H18, choice C, is going to have the highest boiling point. Which one of those do you think would have the lowest boiling point? All right, so I hope these types of sample problems kind of gets you started. This is a very brief introduction into London dispersion forces, but I hope it gives you the nuts and bolts to help you understand the textbook and further problems that you might encounter.